So we continue on the discussion that we have started. That means we have multiple input, multiple output communication system, and we want to achieve diversity gain in the system. So we have a set of complex weight vectors at the transmitter. We also have a set of complex weight vectors at the receiver, and we want to find out the best possible weights that can be put in order to maximize the SNR so that we can get diversity gain. And we'd like to see the performance of such scheme when we choose special weights. And as we have already said, we would like to require some of the tools from linear algebra, which we have summarized in one of the lectures, and would require you to look at some of the fundamental principles. And I have already specified one particular book for that. It's Introduction to Linear Algebra by Gilbert Strang. There are many other books also, but up to your comfortability, you can choose the reference material. So let's continue on what we have discussed in the previous discussion. So we had this particular model that we were trying to set up, and we have this received signal y is mr cross 1, transmit power being divided equally amongst the transmit antennas, and we have already said this is CSI known at the transmitter. So there is this weight which has to be decided, and you can guess it's from the channel, and this is also to be done at the receiver. So this is the equalization that we do at the receiver. At the end of it, we get S, which is 1. We did describe how we get it in the previous lecture. So we move on with this particular description that we have already started. So what we do is we have to maximize the SNR, as we have said. So the expression of SNR, which is gamma combined, we put it like this, would be the Frobenius norm of G Hermitian. When we say y, it will be h times w, right? Frobenius norm squared of that divided by mt. Of course, there is mt times the Frobenius norm squared of G, and you can guess why I am doing this, because if you look at this expression, we are multiplying G Hermitian with y. So if we are multiplying G Hermitian with y, we have a G Hermitian which comes here. This is on the left, so we have a G Hermitian which comes here. We have a G Hermitian which comes here. So G Hermitian HW, the Frobenius norm of that, divided by the Frobenius norm of the weight that comes over here, that is G Hermitian, and of course ES by N naught comes in. ES by N naught comes in, which is gamma bar, and MT comes in. So MT is already here, and ES by N naught that you are seeing would be gamma bar, and G Hermitian that gets multiplied here, G Hermitian HW is already the numerator, G Hermitian is there. So I could have written this as ES by N naught. So N naught times G Hermitian, from this product there would be G Hermitian here. I could write it as G Hermitian here. I could write it as G Hermitian here, right? I could put it that way, and then it will be easier to capture. So this is what we have. So therefore we move on with our expression that we have here. So we have to maximize the SNR at the receiver. So maximizing the SNR is equivalent to maximizing this particular expression, because this is ES by N naught. We don't have much to do with, so we have to focus on this expression, because this also we can't do much, this also we can't do much with. So you have to maximize G Hermitian HW Frobenius norm squared of that by. This could be done in many ways. So what we would be proposing directly, instead of actually deriving through which maximizes, we would like to use the SVD of H. We would like to use the SVD of H. So SVD of H could be U times sigma, some big matrix, times V Hermitian, where this and these are unitary matrices, and this is the singular value diagonal matrix. And of course there is a certain rank of H, so we'll consider that at appropriate time. And by doing this, we could say that this sigma gamma can be maximized when we choose W by square root of MT and G as the input and this as the output singular vectors. So, if we choose them from U and V Hermitian, rather to be precise, if you look at this, I would choose W from V and G from U. In that case, U Hermitian U would lead to identity and V Hermitian V would lead to identity. So, that means if W is chosen from V and G is chosen from U, then we would be left with the sigma matrix. That is, so see the sigma matrix that we have. So, basically I would choose this from this and I would choose this from this. So, that means when we plug it back over here, we are going to get U Hermitian. So, basically we would see this H is broken into U sigma V Hermitian. So, if I multiply here V and if I multiply here U Hermitian, this would turn to identity, this would turn to identity. So, what this would be left with is sigma, and sigma is basically sigma 1, sigma 2 up to sigma r, the singular values, and sigma 1 is greater than sigma 2 is greater than or equal to dot 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 is greater than or equal to sigma r. So, that means we are left with the eigenvalues along with S, and if I choose the vectors corresponding to the strongest eigenvalues, that means if I choose corresponding to sigma 1 and we do not put anything in these. So, then all the power would be in this particular mode, or only on the dominant singular mode. So, this singular sigma I, we remember is related to the eigenvalues of H Hermitian as sigma I squared is equal to lambda I, where lambda I are the eigenvalues of H Hermitian. So, that relationship is also useful to remember at this point. So, what we choose is W and G from these matrices, and we choose them corresponding to the one which produces the sigma max. So, sigma 1 is basically sigma max, and we do not use any other. So, we put the total power into one of them, and that is why this particular scheme is known as the dominant eigenmode transmission, because this is the strongest one. We are not using any others. So, we are using only the dominant mode, and we are choosing this input and output vectors in such a way that it maximizes, and naturally from here we can see that it chooses the maximum eigenmode, and it can be shown that this particular choice maximizes the SNR. So, if we choose that, the received expression after all of this we could write as Z is equal to root over ES sigma max times S times the noise. This is the final expression that you are going to get at the end of it. So, this is the expression. If we choose if we would choose it in this way, you are going to get the expression which is like this. So, when we have it here, we would like to proceed further. So, from this what we have is the received signal Z is equal to root over ES sigma max S plus the noise, and of course, we remember that sigma max squared is equal to lambda max, which we have already said lambda is the eigenvalue of H Hermitian, which is evident here. So, when we calculate the SNR given by gamma combiner is equal to lambda max, because this is squared, times gamma bar. Gamma bar is ES by N naught. So, that is the expression of the combined SNR at the receiver, and since we are using this lambda max in the SNR, therefore, the name dominant eigenmode is even more evident. So, dominant eigenmode transmission, right. So, this, or in short form DEM. So, with this we can carry on, and we could say that this gamma sigma is equal to lambda max times rho, and of course, if we look at this, we can say that this lambda max is equal to this combined by gamma bar. This we will use at an appropriate time. So, since we have I equals to 1 to R lambda I is equal to the Frobenius norm of h squared, we could also say that 1 upon r sum over lambda I equals to 1 to r is equal to 1 by I hf squared. So this again we are going to use. So from this we could say that lambda max would lie between two values. The highest value would occur when there is only one lambda, all others are 0. In that case, this is equal to hf squared. Okay. And the other case, when all of them are equal, or we take the average value, so lambda max is within I equals 1 to r lambda I 1 by r. So lambda max lies between the maximum value and the average value. So this is the range of lambda max. So if this is the range of lambda max, we could say that the average error, or so basically we would take one more step. This is equal to hf squared by r, because this whole thing is equal to hf squared. We already seen that. So basically lambda max lies between hf squared and hf squared by r. Now r is the rank of the matrix. So rank of the matrix means number of independent columns that is there in the matrix, or the minimum of MT and MR. So we would write this as hf squared by minimum of MT MR. This is the rank of the matrix times lambda max is less than or equal to hf squared. So this is what we have. And we have already seen from this expression. From this expression, we could write this as the gamma sigma divided by gamma bar. So gamma bar can go on either side, and we would have gamma bar hf squared by minimum of MTMR. So basically this. So we are saying that the combined SNR lies within this range. So this is a range of within which this gamma sigma lies, and then we can find the range of probability of error from this expression. Now, in case this is full rank, we could say this is gamma bar times max of MTMR. In case of full rank, this is MT times MR. This is MTMR in case of full rank. So if it is MTMR, minimum when divided by minimum of MT or MR, we have the max of MTMR, and this is the range of gamma sigma MTMR. So when it is full rank, this is MTMR. So when H is full rank is equal to MTMR, right, times gamma bar. So if this is the case, we could say that PE bar, which is less than or equal to any bar e to the power of minus gamma sigma d min squared by 4. This is what we have, and we could say that any bar, it is less than lambda max gamma bar d min squared by 4, and it has two range. We have already said the two range values of it. That is, one of the values is hf squared gamma bar d min squared by 4 e to the power of minus any bar. So this is one limit. The other limit is e to the power of minus hf squared into gamma bar into d min squared by 4r. This is the second limit, which we have seen over here. The two limits. This is one of the limit. This is the other limit. Or so basically this r, one is this, one is this. This is the range of lambda max. So with this range, we can calculate the average probability of error, or we can say that the average probability of error would lie in the range of gamma bar d min squared by 4 raised to the power of minus MTMR for the full rank H, and NE bar times gamma bar d min squared by 4 times minimum of MT or MR, or you can bring them to the numerator by saying maximum of MT or MR. So what we are saying is that the average probability of error lies in this range, and which gains in sorry, this whole raised to the power of minus MT MR. So in either of the case, in the exponent we have minus MT MR. Minus MT MR comes from, always remember we are using that E of e to the power of nu Frobenius norm of h squared. This expression is what we are using, is 1 by 1 plus nu lambda r. This is what we are using, I equals to 1 to the size of r. So basically it's MTMR in that case. So the order of diversity that is gained is MT times MR. So that means the full order of diversity is achieved in this, and there is a certain range of SNR which is available, and the SNR, as you can also see, has a range which varies from MTMR times gamma bar to gamma bar times max of MTMR. So this is the gain that you can get from dominant eigenmode transmission, which is again another way of extracting diversity when you have channel state information available at the transmitter. Okay, we continue with our discussion on dominant eigenmode. So we stopped at a point where we could see that the error probability expression for dominant eigenmode has in the exponent MTMR. That means the full order diversity is achievable by using channel state information at the transmitter while having multiple antennas at the receiver as well. So with this, this brings us more or less to the conclusion of the different popular schemes of diversity gain that can be used. There are many other schemes, of course, but we would restrict ourselves to these few things that we have discussed. So with this, we move on to consider the effect of correlation on probability of error. This is very important, because we studied correlation. We have seen how correlation can be captured in the channel model. So in HW channel we have already seen the performance. Most of the schemes that we have seen are for HW channel, and what we'll now see is, if it is not HW, if there is a certain amount of correlation involved, then how does these expression of error probability change when there is correlation involved. So let's move forward, and we will take Rayleigh fading. We will take Rayleigh fading into account, and we remember that R is basically expectation of vec of H times vec of H Hermitian. So in vec operation, we remember, if this is H, it stacks vectorially. So this R is of the size MRMT cross MRMT, or MTMR cross MTMR. So this is the size, it's a big matrix. So typically we could write expression of Y as root over ES by 2 Frobenius norm of H times S plus N. This is usually for the Alamuthi scheme, as you can see that this is typically for the Alamuthi scheme, and the probability of error expression is given by PE is less than any bar e to the power of minus gamma bar d min squared by 8 times HF squared. This we have come across, and PE bar is less than or equal to pi equals to 1 to 4 1 by 1 plus gamma bar d min squared upon 8 times lambda of r, lambda I of r, and that's the product. It's a 2 cross 2 Alamuthi scheme. So what we are interested in is minimizing the probability of error expression. That is what is our interest in. So if you have to minimize the error probability expression, this is as good as you maximize the log, sum of 1 to 4. I take the log of this instead of operating this. If you take the log of this, it's easier. This product becomes a sum. So it is, because this is in the denominator, we would like to maximize the denominator, that will minimize this. So I take the log of it and I minimize this particular term. So we have log of 1 plus gamma bar d mean squared upon 8 lambda I of r. This is what we have, and we also have trace of r is equal to sum of 1 to 4 lambda I of r is equal to 4, again with total power constraint. So this is the total power constraint of the channel that is required. So moving on forward, we would like to see that the error probability expression Pe bar is given as less than or equal to any bar times gamma bar d mean squared upon 8 raised to the power of rank of r, right, because you have this pi in case of correlation. We're going to 4, assuming there are 4 independent branches. That means these values are all non-zero values. Now if there is some kind of correlation, it won't be a 4 order matrix. The rank would be less than that of MTMR. So we want the rank of R, so it could be less than that if there is certain amount of correlation. And if we look at this expression, we are taking the case where gamma bar is stronger than 1, much stronger than 1. So we are neglecting 1 in this expression, and we have already raised this to the power of minus r. We have taken it out of this product sign. So we have the product of lambda I of r to the power of minus 1, I equals to 1 to rank of r, right. This is in the denominator. So we have basically neglected 1 that is over here to simplify our results that we have here. Now we should remember that this thing is maximized. This thing is maximized when if you look at this, either this expression or from this expression, it can be achieved from both the cases. This thing is maximized. We want to maximize this when all lambda i's are equal to lambda. So when they are all equal, then this gets maximized. This can be verified for all I. So this can be verified separately. So that means this is maximum when all lambda i's are equal. That is for HW channel. This is true when the channel is HW. That means a spatially wide channel. Now when it is not spatially wide channel, R is not equal to I matrix. That means the covariance matrix is not equal to identity matrix. This is not true. If this is not true, then this is not maximized. So that clearly means that when we don't have a spatially wide channel, the error probability is not maximized. Sorry, the error probability is not minimized. So something else happens. So that means from this side also we can see it is detrimental. Now let us see further what we have in this particular case. So we would like to recall the arithmetic mean geometric mean inequality, from which we can say that 1 upon m sum over I lambda I of r is greater than or equal to geometric mean I equals 1 to m lambda I of r raised to the power of 1 upon m. So this is geometric mean, this is the arithmetic mean, and so we could say that pi I equals 1 to m. Now since this should be equal to m, lambda I of r raised to the power of 1 upon m is less than or equal to 1. This is what we are just bringing it to the left hand side, because this thing is equal to m because of total power constraint. So this thing should be equal to 1. This is less than or equal to 1. So in other words, pi I 1 to m, that means product lambda I of r is less than or equal to 1. So if that is less than or equal to 1, what we have over here is this particular product is less than or equal to 1. So there is a minus 1 in the numerator, if you see. So that means the denominator is less than 1, this whole product. So this whole term is increasing. So it is more. So we are multiplying it by a term which is more than 1. So that clearly indicates that this is increasing the probability of error, and this is with equality. This holds with equality when on all lambda i's are the same. So from this, what we can also gather is that the error probability Pe bar is affected negatively by correlation. So what you get the double effect that error probability increases because of this is less than or equal to 1, and secondly what you get is this is raised to the power of r, the rank of r. So that means if rank is less than MTMR, then this exponent is also less, this exponent is less, as well as this term adds to it. So overall PE bar increases when compared to a specially wide channel. So in summary, we can say that if there is correlation present, the probability of error is affected in the negative way. Moving on forward, what we'd like to add is suppose we have a Rician effect, a Rician channel. So if you have a Rician channel, that means there is an LOS, or expected value of the channel coefficient. There is some mean value of h, that means non-zero mean. This we have described earlier for the flat fading. Now we have the matrix, that means each element of them they are non-zero mean, and we could say that h is equal to square root of k, the Rician component, which we have described thoroughly in our description of channel coefficients, and 1 plus k times hw. So we have a line of sight component and we have a specially wide component together forming a Rician channel. In this case, we have the probability of error expression given as probability of error expression less than 1 plus k divided by 1 plus k gamma bar. This is the power branch SNR divided by 8 raised to the power of 4 to the power of minus 4 gamma bar d mean squared k mod hf squared divided by 1 plus k plus gamma bar d mean squared upon 8. So this is the expression for it. So as k tends to infinity, that means as you get more and more stronger line of sight component, and this is hardly anything, that means we have an antenna and there is only direct line of sight, there is no scatterer around. So you can imagine a satellite communication or a microwave link. In that case, what's happening is of course we're talking of multiple antennas. PE bar is less than or equal to, as k tends to infinity, this converges to the expression minus gamma bar d mean squared by 8 mod hf squared, right? And that means it is tending more towards a line of sight or more towards a non-fading condition. And so that means when you have a Rician channel, the moment you have a Rician channel, that means you are stabilizing the link. So as your k component increases, there is hardly any component over here, and as there is line of sight component, this component is the mean of it. So this component is the mean of it. So what you see over here is the mean component over here, which is a fixed number. Everything is a fixed number. So the error probability expression that you get is becomes a fixed number. So that means the link is stabilized. There is no variation in the link, and it is almost like an AWGN channel. So what we have seen is that when there is diversity, even without array gain, as you increase the diversity towards infinity, your performance behaves like AWGN, or it meets AWGN. And the last case what we saw just now is when you have a Rician component, then as the Rician components become stronger and stronger, your link stabilizes, and that is also logically straightforward. You are receiving direct signal from the antenna, and there is no fluctuations at all. So there is no variation. So link is stable. We have also seen that if there is correlation in the channel, then also then the effect is that your error probability increases in two effects. One is that the product of the eigenvalues is less than 1, which is in the denominator, and therefore it increases the error probability. And secondly, the exponent of average SNR is also not MTMR, or not the full rank for capital R, which is the covariance matrix. It is rather the rank of capital R. So if rank is less than the full rank, your exponent is less, you have less diversity gain, as well as you have a shift in the error probability expression as well. So to summarize, we can say that diversity gives you improvement in error probability, correlation decreases the gain of diversity, or it increases error probability compared to a HW channel, and if there is a line of sight or Rician component, you can also say that the link becomes stable and there is no fluctuations. So it becomes more or less like an AWGN with an appropriate gain. So I would like you to summarize these important conclusions, and we'll make this as one of our last lectures on diversity. After this, we'll move on to look at spatial multiplexing or the channel capacity of MIMO systems. Thank you.